So good evening, everyone. In the previous lecture, we just discussed about the hypothesis testing under the parametric bootstrap methods. So today we will start with the non-parametric bootstrap test. All right. So the challenge that we have, how to generate the data under H naught without parametric assumption. The thing is that uh, if we don't know the distribution of our data, okay, for our given data, xi, that we usually assume that it was following some particular distribution with parameter theta or parameter mu. Right now, we do not know what is the distribution exactly. All right. So, how we will generate the data to test the null hypothesis? All right. So, the solution is to transform the observed data so that it satisfies the H naught, then resample from the transformed data. That is the only possibilities that we have here. So what we need to do and how to transform the data. So first of all, we are subtracting the X bar to center the data at 0. They will give us some non-parametric data, say x1, x2, up to xn data they will provide us, and corresponding to that, if x bar is the corresponding mean, all right, so what we will do, we will subtract this mean from each observation to center the data at 0. All right, after that we will add mu naught here under the given under the h naught, okay, given under the h naught, to shift the center to the null values. All right. So this transformation preserves the shape of the empirical distribution, means variance, skewness, and kurtosis, while aligning with its mean, that is mu naught. All right. So the transformed data set, that will be our, you will say, xi naught. This will be our transformed data set, that is xi. From each observation, we will subtract the mean, observed mean, and add the null hypothesis value mu naught. All right, for all I go 1 to up to n. All right, so that will be this transformed data will be our best non-parametric estimate of the population under the H naught. All right, so after that, in the second one, we will check, or we will verify that whatever the transformation we did, it is working properly or not. So in that one, we check the centered mean exactly to the mu naught or not. So in that one, what we will do, we just find out the mean of I goes to 1 to n xi minus x bar plus mu naught. We will find out that one. So when you will apply the summation inside, what will happen? It will becomes 1 upon n summation over the range of I xi plus, sorry, minus x bar is a constant term. So when you will apply the sum on that one, so it will becomes 1 upon n into n x bar, right? And plus 1 upon n into mu naught, because mu naught is also a constant value. So these n's will be cancelled out, and this 1 upon n summation over the range of I xi will be x bar. So it will becomes x bar minus x bar plus mu naught. So that will be cancelled out. So you will have the mu naught. All right. So that's how it will satisfy. So in the next step, bootstrap from the centered data. So what we are going to do, we will draw the bootstrap samples from the this centered data, and this simulate the sampling from a population that satisfied the H naught. All right. in that one, again, after that, for each bootstrap sample, we will compute the mean and the deviation from the mu naught, and this will provide us the bootstrap null distribution of the test statistics. All right. After that, in the fourth step, what we will do, we will compare our T observed that we discussed in the previous lecture to the bootstrap distribution and include the plus one correction. All right. So that is our non-parametric bootstrap test. So this is the code for non-parametric bootstrap test. So we will discuss about this one. All right. This code. All right. This is the R code for our non-parametric bootstrap test. All right. Suppose in X we have the non-parametric data set. All right. So here X provides the 12 observations here. All right. And this is the sample that we want to test. And after that, we have the n equals to length of X. That is the length of the sample size that is stored in X, and X bar is the mean of the X bar is the sample mean of the original data set. And after that, we have defined mu naught equals to 12. That is the null hypothesis. All right. This is the mean under the null hypothesis. So set the hypothesized mean under H naught, that is 12. So after that, we will find out the centered value of X, that will be X minus X bar plus mu naught. All right. So we will run it and we will check the centered values. All right. These are our centered values. Okay. For the given data set. After that, we are going to apply the resampling about 9,999 times. All right. And after that, we are describing T star as a null vector, okay, of length capital B that will store the bootstrap test statistics. All right. After that, we are going to apply the for loop of B number of times here. In that one, in X star sample, X centered values, we are going to generate, okay, we are going to generate a bootstrap sample of size n from the shifted data that we stored in the X centered with replacement, and this is a non-parametric part. So we resample from the empirical distribution that satisfied the H naught. All right. After that, in the B star capital B, we are going to compute the bootstrap test statistics, that is the difference between the bootstrap sample mean and the null values. Okay. Under the H naught, the mean of X star should be centered around mu naught. So T star approximates the sampling distribution of the test statistics when the null hypothesis is true. All right. So after that, we will close the bracket. We will stop the our for loop. Okay. And for two-sided p-value, so we observe the test statistic is the simply the difference between the original mean and the null value, and p-value will be sum of absolute of T star that is greater than equals to the absolute value of the T observed. All right, plus 1 divided by B plus 1. So we count how many bootstrap statistics are at least as extreme as the observed one in the absolute values. All right, here, okay, it creates a logical vector and sum counts the number of truths and plus one in the numerator and the denominator is the common correction, that is the Davinson Hinckley correction that I told you in the previous lecture, to avoid a p-value of 0 and to account for the Monte Carlo error. So it effectively include the observed statistics as the part of bootstrap distribution. All right. And the resulting value is the estimated bootstrap p-value for testing the H naught, that is mu equals to 12 against the alternative hypothesis, that will be your H1, such that mu naught equals to 12. All right. After that, we will call the output. So in that one, in these two commands, what we are going to do, we are going to print the observed sample mean in the first one, okay, and rounded the values in two decimals and the bootstrap p value here in that second command. We call the bootstrap p value and rounded it to the 4 decimals. All right. So if p value is less than 0.05, it will indicate that the null hypothesis is rejected. Otherwise, we will accept it. All right. So now we just run the remaining part of this code. All right. So p value is almost 0, that is 1 e raised to the power minus 0.4. All right. So that is less than 0.05. So we are going to reject the null hypothesis because the observed mean is 13.29. Okay. So this entire code implements the non-parametric bootstrap testing, hypothesis testing for the mean, and it shifts the original data to have the mean equals to the null value and preserving all other characteristics. All right. So bootstrap samples are drawn from its shifted data set, and the test statistics is recomputed each number of times. All right. So that was the R code for your non-parametric bootstrap test for the mean. Now we will go for the further. Again, we have the two sample comparison. Okay, two sample comparison we are having here. So in that one, that is basically treatment against the treatment versus the control. So here, what we basically are doing, we have the question is that here, is there a difference in the mean response between two groups? All right, give me a second. Testing. Okay. So is there any difference in the mean response between two groups or not? So that is the question here. All right. So in that one, what we are going to do, we have the data set. In that one, we have the treatment where we have the number of observation n1 is 15 and x1 bar is 24.5 and standard deviation is s1 is equals to 4.2, right? Similarly, for the control, we have n2 equals to 18 number of observations and x bar 2 that is equals to 21.3, and s2 the standard deviation for the second sample is 3.8. So the hypothesis that we need to check, or tested, that is H naught such that mu1 equals to mu2 against the alternative hypothesis H1 such that mu1 is not equals to mu2. And we observed the differences, that is x1 bar minus x2 bar is basically 3.2. So we need to use the bootstrap approach here. So under H naught, pool the data means group the same data, then randomly assign the two groups to the of sizes n1 and n2 and compute the differences in the mean and repeat b number of times. All right. So what we exactly need to do here? So the algorithm will work like this: two sample, test for equal means, right? So the algorithm will be, in the first step, what we need to do. So it will be a non-parametric bootstrap test under the H naught mu1 equals to mu2. All right. Non-parametric bootstrap test for H naught such that mu1 equals to mu2 against the alternative hypothesis H1 such that mu1 is not equals to mu2. All right. So in that one, the in first step, what we need to do, we need to pool the data. Okay, pool the data in such a way that combine all observations from the both groups into one set. All right, combine all observations from one group, from both groups, from both groups to into one group. All right, that will be look like x1, x2 up to x n1 plus n2. Okay, so that will be your data set. And now after that, in the second step, for the loop, that is your, for b, that is 1 to up to capital B times, that will be approximate to 10,000 times. All right. So in that one, draw the bootstrap sample of size draw the bootstrap sample of size n1 plus n2. All right, with replacement from the pooled data. All right. After that, randomly assign in the second stage randomly assign the first n1 observation, first n1 observations to first group, okay, to first group or group 1, and the remaining n2 n2 to group 2. All right. And after that, in third step, compute their differences. Okay. Compute the differences. All right. In the mean, that is basically D star B equals to x1 bar star B minus x2 star B. All right. Basically, what you need to do, if I just tell you here up to here, when you have the data set, say x1, x2 up to xn1 data set you have, and another data set that you have, that is xn1 plus 1, xn1 plus 2 up to xn2. This is your data set. All right. Or you can say it as 1 to up to n2 also, but for the simplification, I am just telling n1 plus 1 and 1 plus 2, and this will be n1 plus n2. This is your entire data set. So we are going to combine it into one data set that will be x1, x2 up to xn1 plus n2. After that, we will generate the random data from this one again of same size n1 plus n2. So it will be x1 star 1, okay, x2 star 1 up to x n1 plus n2, oh sorry, star 1. All right, so this will be your one data set. After that, you need to split it. Okay, so the first n1 observation from here, that will be x1 star, sorry, x1 star 1, x2 star 1 up to x n1 star 1. These observation we will keep as our first data set. It will be our group 1, and the remaining values from here, that is x1, x2 up to x n2 observation, that we will have x1 star 1, x2 star 1, x n2 star 1. These observation we will consider as the group from group 2, and then we will compute their mean. Okay, x1 bar star 1 and x2 bar star 2. All right, sorry, bar 1. And we will take the differences of that one, both of them, that will be d1, right? And here we are not saying it d1, we are saying it d star 1. It will be x1 bar star 1 minus x2 bar star 1. All right. So that will be our differences, and we will repeat it capital B number of times, and we will compute the mean differences again and again. After that, in that is 2. So now in the third step, sorry. In the third step, we will compute the two-sided p-value. Okay, compute two-sided p-value, that will be small p equals to the number of sum of the number of observation that where the bootstrap differences capital D star B, the absolute value of that one of that differences is greater than equals to the D observed, the actual observed value, all right, plus 1 divided by B plus 1. All right. So where D observed is basically the actual differences of the mean from the original data, that is x bar 1 minus x bar 2. All right. So we need to compute the p value as the sum of the total number of observations of our differences of the mean, the absolute value of the differences of the observed mean that is greater than the observed mean from the actual value. All right. So that is our basically pooled what we said, two sample comparison method under the non-parametric approach. All right. So here we have two assumptions. Sorry, we have the three assumptions for this one. First is for the one sample test, for one sample test, the data should be IID. The data should be IID. It means the transformation assume that the under echelon the entire distribution is shifted by a constant. Okay, so this is appropriate for the location shift, but not for the scale or the shape changes. All right. So, and the second assumption for your two sample test. So, for two sample test, under the H naught, the two population are identical. Okay. Under the H naught, two populations are identical. Okay. And not just equal means. All right. So if variances differs means heteroscedasticity is there. So the pooling will shorted the variance. Okay, variance structure, and the test may not be valid. So in such case, a wild bootstrap or a test based on bootstrap standard error may be preferred. All right. And third assumption is that exchangeability should hold. All right. Exchangeability holds. All right. So under H naught, the observations are exchangeable between groups. All right. So what we were doing, we were taking, if you just see here, we had the both observations were there, x1, x2, xn1, and xn1 plus 1 up to xn1 plus 2 up to xn1 plus n2. So after combining both of them, when we are going to generate the sample. So in this first N1 sample, it is not necessary that all the observations that will occur, they should come from the first group. Some observation may come from the second group also. All right. And similarly, in the group second that we are going to divide here, the next N2 values that we are having, it is not necessary that all the observations that will occur here in this second group that we are creating after resampling, all the observation will come from the second group, original second group. Some observation may come from the first group also. All right. So that is called as the exchangeability. That should be happen here. All right. So that is the important thing for the your two sample comparison. We have the one R code here for that one. So check the two sample bootstrap. All right. So suppose here we have two observations we are having. All right. So in that one, treatment and control, in these two vectors, we have observation. In treatment, we have the 15 observation, and in control, we have 18 observations. These represents the measurement from two groups. For example, a treatment group and a control group in an experiment. All right. After that, we have the N1, that is the length of treatment, and N2 is the length of the vector of control. All right. And N1 and N2 will store the sample size of the treatment and control groups. And after that, we have the observed difference. So in the observed difference, we observe that test statistics, the difference between the sample means of x bar of treatment minus x bar of the control. All right. This will quantifies the effect of observed in the original data. So after that, pull the data under H note. So in the pooled, we are going to combine treatment and control by applying the C for the combined. All right. So we are going to pull the two samples into the single vector of length. Now the length will be 15 plus 18, that will be 33. So under H note, all the observations come from the same population. So pooling is justified here. All right. So N is the total number of observations. All right. Capital N is the total number of observations. After that, in capital B is the number of random shuffles or the resampling, that is 9,999 times, as we had done earlier. That is a typical choice for the Monte Carlo test. So after that, in the boot differences is a numeric empty vector, okay, of length capital B, that will store the differences in the mean from each resampling. And after that, we will apply the for loop here. In the for loop, we have the shuffled, that is the sample, okay, from the pooled observation, that is randomly permutes the pool data. This is equivalent to the randomly assigning the original observation to the treatment and the control groups, but without changing the group sizes. Okay. So under H note, any such assignment is equally likely. Okay. So after that, we are finding the boot differences. Okay. In that one, we have the mean of shuffled uh, the first n1 elements are the shuffled vector are treated as the treatment group, and the remaining n2 here, okay, elements are the control are will be treated as the control group, okay, and the differences is the mean. The differences in the mean is computed for this. Basically, we will call it the artificial split. All right, sometimes. So the result is stored in the bth element here, okay, of the boot differences. So after the loop, boot difference will contain the empirical distribution of the differences in mean under the null hypothesis. Okay, so that means when the group will labels are randomly permuted. So after that, we are going to calculate the p-value. In that one, the absolute difference of the boot difference greater than equals to the absolute of observed boot difference here creates the logical vector, again indicates the which bootstrap differences are at least as extreme as the observed differences in the absolute value. So this is the appropriate for the such values occur, and again +1, you already know that I described it a number of times. All right. So the result is estimated probability under H naught of observing a difference in mean whose absolute value is at least as large as the absolute observed differences. Okay, after that we will print the output here as we have done earlier, the observed differences and the bootstrap p-value. So we are printing the bootstrap differences up to the uh, two decimal values after the decimal, and for p-value we are printing for the four values, four decimals. Okay, so we will run this one. Okay, so object difference is 3.66 and p-value is again 1 e raised to the power minus 04. All right. So this code performs the two sample randomization test, often called as the permutation test, for the differences in the mean. So by repeatedly shuffling the pool data and recomputing the differences, it will build the null distribution of the test statistics under the assumption that the group labels are exchangeable. Okay, and the p-value is the proportion to the shuffled differences that are extreme or more extreme than the observed differences with a small sample adjustment. Okay, so this method is a non-parametric method, and it makes no assumption about the normality, and it is valid for the any distribution as long as the observations are independent and exchangeable under the H note. All right, so this was your R code for two sample. Okay, now we will go for the testing of correlation. Okay, so question is that is the correlation between x and y are significantly different from zero, okay, or not? So suppose we have the data of a sample size n equals to 20 paired observation, and their correlation, exact correlation is 0.42, and in that one hypothesis will be h naught such that rho equals to 0 means both of them are independent, against h1 such that rho is not equals to 0 means they are dependent. So after that, if rho equals to 0, then x and y are independent, and to simulate that we will keep the x values are fixed and randomly permute the y's value, means breaks any relationship and compute the correlation of x comma y permuted. Okay, so this is actually a permutation test. Again, as we have done earlier. All right. So the entire command or entire algorithm will remain same as the we have done in this algorithm of two sample test for equal means. Okay, but we will keep the vector x as a fixed values, and we will generate the values of y again and again here. All right. So here we have the R code for that one again. So this R code is for the permutation test for the correlation. We will discuss all these permutation tests in the detail. All right. So in that one, suppose we have n equals to 20 observations are there, and we are generating x from the normal distribution. Okay, 20 observations from the normal distribution, that is the basically comes from the standard normal distribution with mean 0 and variance 1. And after that we are assigning the y in terms of the linear combination of x. Okay, so y is created as the linear function of x plus independent normal error. So the coefficient 0.4 and the standard error with sorry, not standard, the error in this relation with standard deviation 0.9. Okay, so both of them are chosen so that the true population correlation is approximately to 0.4. That will create a non-null data set for our example. All right, so we will try to run it, and we check it. The observations of x are these values, and observations in y will be this. All right, and after that we will calculate the correlation between both of them. That will be the by the command core of x comma y that computes the sample Pearson correlation R for the generated data set, and we will store it in observed underscore of correlation. So the values will be 0.08394. So it will change again and again as the sample size will change. All right. So if I want to generate it again, I will check it again. Now check it. All right. So it will change every single time when my observations will change. All right. Observation of x, as the observation of x will change and this random error will change accordingly, the correlation will change every single time. All right, because this is a simulation study. All right, in that one we are calling the observed correlation. Here we are printing the correlated observation correlation. After that we are going to run the bootstrap up to 999 times, and we are going to introduce an empty vector boot underscore core where we will store the correlation values. Okay. After that, we will apply the for loop again as we have done earlier over the B permutations, and in Y underscore perm, we are going to generate the sample of Y every single time. Okay. Of the same size n, we don't need to introduce here. It will take automatically that one. If you want to introduce n and the application equals to true, that you can do. Otherwise, no need to do that. All right. So after that, we will call the boot underscore correlation. Okay, that will compute the correlation between x and the y permuted values of the y. All right. And it will store in the boot underscore core. All right. After that, we will stop the for loop and we will calculate the p value of the correlation. Okay. It will be two-sided p value. So in that one, we just check the, as we have done earlier, we call the number of observations of correlation, sample correlation, where the absolute value of the correlation of bootstrap is greater than equals to the absolute value of the observed correlation. All right, after that we will uh, print that bootstrap p value, and after that we will apply the classical test, the correlation test on x and y, and we check the classical p value under that one of up to the 4 decimal points. So we just check it. Okay, so the bootstrap p value is 0.0053, and for the classical correlation test, the p value was 0.006. So they were almost similar. All right, if you will increase the replication, it will be almost similar values you will get. All right, so that is the test for your what we call it, correlation. Okay, do you have any doubt till here, or should we proceed? Should we proceed, or do you have any doubt? Okay, so we proceed here after this. So the power of the bootstrap test. So I hope all of you know the definition of the power of the test in testing of hypothesis. So definition says that power is basically 1 minus beta, that is equals to the probability that reject H naught when H1 is true, right? So the properties of the bootstrap, power of bootstrap test is that generally it is comparable to the classical test when assumptions hold, and can be more powerful when the classical assumptions fail, and the power increases with the sample size and the effect size. All right, so in the classical test, for example, a t test, f test, so the classical tests rely on the specific parametric assumption that the assumptions of the normality and homogeneity of the variances and known sampling distributions. And violations of these assumptions can reflect type 1 error, and or it can reduce the power of the test if these assumptions are going to be violated. So, but in the bootstrap test, it requires only the minimal assumptions, typically the exchangeability, okay, under the H naught for permutation test, or the ability of resample in a way that it will mimics the data generating process, and this flexibility makes them applicable in a wide range of the settings. All right, and the second thing that is needed here, the exact null distribution. In classical test, we use the theoretical distributions like t test, f test, or chi-square distribution, t distribution, f distribution, or chi-square distribution, which are exact only when the assumptions hold. But in practice, they are approximations. They are in the approximation, exact sampling distribution, theoretical distribution, we rarely get. All right. So, but in bootstrap test, we simulate the null distribution empirically. Uh, so the permutation test provides an exact conditional test, and Monte Carlo approximation can achieve any desired distribution. Okay. So for the complex statistics, like for non-standard statistics, like mean differences or the ratio of the variances, or truncated means, or that we have done like correlation test. Right now we did the classical sampling distribution are most of the times are unknown. All right, but in the bootstrap method, we can handle any statistics that can be computed from the data, and simply we can do it by recalculating it or resampling the data sets. All right, but another thing is there in that one. The classical test may perform very poorly in the small samples when the assumptions are violated. All right, but permutation tests are exact for any sample size under the exchangeability. The condition exchangeability should hold there. Other bootstrap variants, for example, percentiles bootstrap, may have coverage error in small samples, but it will outperform in the parametric methods when those are misspecified. All right. So, but in that one, there is a one problem that will be the computational time. In the classical test, you don't need to resample again and again, but here you have to resample again and again. So it will take the time, a lot of time to recompute. All right. So, so the power of the bootstrap. All right. Bootstrap test. That is the probability of correctly rejecting a false null hypothesis. It depends on the true effect size. Okay, the power of the bootstrap test, that is always depends on the true effect size, sample size, variability, and the significance level of alpha. uh, the properties of this one is, when classical assumptions are made, the bootstrap tests, especially the permutation test, are asymptotically equivalent to the classical test. So power is comparable at that time. All right. If assumptions fail, so a bootstrap test using a robust statistics that can be more powerful than a classical test that relies on the normality. That is the another thing. Okay, like any consistent test, power increase with the sample size and the effect size. All right, so how you will increase that one? So generate a data set under the alternative hypothesis with a specified effect size, and in that one, when you have the nested simulation, that will increase the power of the test, nested or resampling, double resampling bootstrap methods we discussed earlier. In that one, you need to generate a data set under the alternative hypothesis. Okay, and for the inner loop, you need to generate the data set from that outer loop resampling, and run the bootstrap test again and again to obtain the p-value, and compare that p-value to the alpha, and record the whether h naught is going to rejected or accepted. All right, and repeat outer loop a number of times. Okay, means 10,000 times or 20,000 times, like this. Okay, so apply to check the power of the bootstrap. Always just remember, eval before checking the power, you should or you must verify that the bootstrap test maintains the nominal type 1 error rate under the H naught. All right. And second thing is that the number of inner bootstrap resamples B, capital B, affects the accuracy of each p value. So too small, capital B, okay, too small number of replication can bias the power estimates. All right. So for hypothesis testing, permutation tests are often preferred because they give the exact type 1 error control. Okay, condition that is basically called as the conditional on the data and are straightforward to implement. All right, this is the thing that you should always remember. All right, so that is your power of bootstrap test. Okay, now we will discuss about the permutation test. Okay, do you have any doubt till here in the power of bootstrap test or anything, or should we and we should proceed? If you are okay, so we should proceed for that one. Permutation test. Should we proceed? Okay. So that is the last part of our bootstrap. Okay, that is the permutation test, jackknife, and the cross validation. All right. So what are the permutation tests? So a permutation test, that is also called as the randomization test, that determines the p-value by calculating all possible values of the test statistics under random rearrangements of the data. All right. So basically, permutations tests that are also known as the randomization test are a class of resampling methods that are relying on the rearranging the observed data to assess the significance of the test statistics. Unlike the parametric test like t-test, ANOVA, and others, so they do not assume a specific distributions for like normality assumption for the data. Instead, they drive the sampling distribution of the test statistics directly from the data by permuting the group labels or observations under the null hypothesis. All right. What is the core idea basically behind it? The core idea is to compute the test statistics for all possible assignments of the data uh, to groups or to conditions that are consistent with the null hypothesis. For examples, in a two sample problem, if the null hypothesis states that the two groups come from the same population, then we can rearrange these groups labels among the observation equally. Okay, and the p-value is then the proportion of these permutations that provide a test statistics as extreme as or more extreme than the one observed in the original data. All right. So basically, we are going to, if interchangeability or exchangeability are allowed inside the group, so we can apply the permutation test. All right. So when all permutations are calculated, so the resulting test is exact, and then the p-value is not an approximation but a exact probability under the null hypothesis. So this property holds for even for the small sizes of sample, and that provides the exchangeability assumptions is under the consideration. Okay, this property holds even for the small sample sizes. Okay, in generally when the number of permutation is extremely large, all right, means for example n1 plus n2 are chosen, okay, very large, so we resort the random subset of the basically called as the Monte Carlo permutation test to obtain the approximate p-value. All right, so this permutation test was given by R.A. Fisher in 1930s. All right, and the idea behind of that was basically uh, for the to test the non-parametric to sample and resampling. Okay, that will include the bootstrap methods. So the key idea here, that we are discussing again and again, that is the idea of exchangeability or interchangeability. All right. So this is the main assumption for the permutation test. Exchangeability means that under the null hypothesis, the joint distribution of observations remain unchanged when the group labels are arbitrarily permuted. Okay, so in a very simple manner, if the null hypothesis is true, so then the data are essentially one homogeneous set, and that objects grouping is just one of the many equally likely ways to partition the data. All right, so means we can combine both of data set and we can generate the sample from them. All right. How you will say it means if you have x is a one variable, that is x1, x2 up to xn. All right, and you say xn1, and you have y, that is y1, y2 up to yn2 observations. In that one, the alternative, null hypothesis is basically defined that both of them affects the distribution of both observations are equal and identical. All right, means they are coming, both samples are coming from the same distribution family. All right, and then they combined, and then any combined sample of size n1 plus n2 observations. Okay, we generate the sample. Okay, so exchangeability is weaker than the independence, so it is only requires that the joint distribution is symmetric in the arguments. So in many experimental designs, if the subject under the study are randomly assigned to the treatment, exchangeability holds under the null hypothesis. Okay, so however, if there are hidden structure like clustering or other things, so exchangeability may be violated unless the permutation scheme is appropriately restricted. Okay, so at that time we just go for the block permutation. Okay, that you have studied in that one design of experiment. All right. So why we are calling it the randomization? In a randomized experiment, the physical randomization justifies the exchangeability. So the permutation test, then the permutation test can replace or can be look like a randomization process that makes it the randomization test in the very strict sense. Okay, this is that's why the term we oftenly use, that is basically interexchangeability or exchangeability or interchangeability and randomization. Okay, so the null hypothesis here, the groups are exchangeable. The interpretation of this group, this null hypothesis is basically if the treatment has no effect, then each observation or each subject under the study would be same regardless of which group they are assigned to. All right, it doesn't matter from which group they are coming, they are same. So consequently, the observed data could have comes from any random allocation of the subject under the study to the treatment and the control group. All right, so hence the group labels are arbitrary and can be permuted without changing the underlying reality. Okay, so this is the basically your permutation test. All right, so after that we can extend it up to the two sample test also, and it is very important in the non-parametric nature. because they are free from any parametric assumption, normality, homogeneity of the variance, and that may be useful for the small samples. All right. And in the if we don't have the exact inference at that time, it will be very useful, and it is very useful for handling the complex design of the data. Means permutation method can be adapted to the various designs like paired sample, block design, or time series by restricting the permutation appropriately. All right, so this is the importance of the permutation test here. Okay, now comes to the historical background, that is the Fisher's lady testing. So that was the original permutation test that Fisher applied in 1935. So he claimed that a lady claims that she can tell whether milk was added before or after tea. Okay, so in that one, they had the 8 cups, 4 with the milk first and 4 with the tea first. Means in the 4 they add the first they add the milk, and they after that they add the tea, and 4 cup they had where they added the tea first and then they added the milk. Okay, so result, she correctly identify all 8 cups. All right. So Fisher's question was that what is the probability of this by chance? So calculation was total possible arrangements, that will be 8 by 8c4. Okay, so that will be equals to 70. So basically the lady claims that she can genuinely find out that uh, and she can sense the she has the ability to discriminate between two preparations methods of tea, that is the milk first or tea first. All right, so alternative hypothesis in that case was that the lady can identify the order with the better chances accuracy, and the null hypothesis was that lady is genuinely guessing the which or you can say the under H note, her probability of correctly identifying a cup's preparation is exactly 1 by 2. All right, and her overall performance is no better than what would be expected by chance. So that is the basic concept. All right, and this example is published in R. A. Fisher's book. That is, the title of that book was Design of Experiment. All right, so that was the example. If you want to read it, so you can read it in that book in the detail. So now we comes to the mathematical framework of this method. Okay, so we have the two groups here, group 1 x1 x2 xn1, and group 2 y1 y2 yn2, treatment and control, and pull the sample and find the t statistics there. Okay, so like the differences that I told you earlier. Okay, all these steps I told you in the previous one. All right. So after that, we have the permutation distribution here. So under the H naught, no group differences. So all NC and 1 assignments are equally likely. So the permutation distribution is T pi such that pi belongs to the script P, where script P is the set of all possible permutations of the group labels. So basically, the permutation distribution is the set of all possible values of the test statistic T computed under the every possible permutation pi of group label. All right, for each permutation pi, we reassign the labels to the to the pulled data, that is basically Z, okay, x1, x2, n1, y1, y2, yn, and recompute the test statistics T. All right. This represents the collection of M equals to N, C, N1 numbers. Okay. So in the practice, M should be very high. All right. So this mathematical expression T pi such that pi belongs to the script P is basically let pi be a permutation of the indexes 1 to n. Okay, 1 to n, that determines a new label vector, that is suppose L pi, then T pi, that is your test statistics, is basically equals to the function of T, Z and L pi. Okay, so thus this set T pi such that pi belongs to the script P is the reference distribution for the test statistics under the null hypothesis. Okay, this will call as the reference distribution. All right, because here we are we we are computing all possible assignments, or you can say all possible groups of the pool data set. The resulting p-value is the exact for the observed data and condition that will be conditional on the data under study, and there is no approximation error from the asymptotic theory. All right. So observed statistics, the T observed correspond to the original labeling. Okay. That is basically L observed. All right. So now we will go for the algorithm, Bootstrap, permutation test algorithm. So in that one, in the step first, we compute the observed test statistics here from the original data. All right. So T observed here, T observed is basically is the value of the chosen test statistics calculated from the original and unpermuted grouping of the data, that is the basically original one, x1 x2 up to xn1 and y1 y2 up to yn2. All right. And for a two sample problem, the common choices includes the differences in the sample mean x bar minus y bar and t statistics, or differences in the median or any other uh, statistics and, of interest that we choose here. The choice should reflect the alternative hypothesis. Okay, for example, like a location shift or the scale changes. Right. So T observed use as the original benchmark against which we compare every possible value of the statistics from the from all permutations. Okay, so in the permutation framework, we condition on the data, and the only randomness comes from the allocations of the labels. And the second step, what we are going to do, we have the we calculate all NC and one possible assignments. So we consider every distinct way to choose N1 observations out of pooled N. Okay, out of pooled observations N, that is N1 plus N2. How many total ways to choose N1 observations? Okay, because what we are going to choose, N1 observations from total observations, and remaining we are going to use as the N2. If you remember that we did in the previous example. So we need to find out N1 observations from N1 plus N2 that we will label as the group 1, and remaining observations we will label as the group 2. Okay, and that will be automatically we will do. We need to focus on the N1 only. All right. So each such choice correspond to the possible labeling. The total number is given by the of as a binomial coefficient, that is basically m equals to n, that is basically n1 plus n2 cn1. That is the only possible ways. All right. So under the null hypothesis H naught, that is basically the two groups come from the same distribution. Every assignment of the label to a fixed data values equally likely. All right. This is the exact null distribution of the test statistics with no approximation. All right. And here you should remember that we are not resampling the new data. We are reshuffling from the existing observation. Okay. So full full study or the complete study is only feasible when m is not too large. All right. That we can do. Complete study we can do when m is not too large, means the combination number of combination is not too large. At that time we can do that one only. All right. For each permutation pi. Okay, so first assign n1 observation to the group 2 and compute the t test statistics t pi. All right, as we have done in the previous part when we were doing for the two sample two sample null hypothesis test for the mean. Similarly, we will do here, and then we calculate the p value. Okay, so p value is little bit different from the previous methods that we were doing. Here, what we are doing in the numerator, we are calculating how many permutation statistics are as extreme as or more extreme than the observed statistics t observed. Okay, and the denominator is the total number of permutations. So what will happen at the time? The p value is the proportion of the label assignments under the null hypothesis that represent a test statistics at least as extreme as the one we can actually observe. Okay, so the inequality greater than equals to implies the one-sided test in this direction, in the direction of the large values of t. So for a two-sided test, we need to measure the extreme side in the both tails. All right. So at that time, what we need to do, the p will be the sum of the total number of observation will be becomes the absolute test statistics t pi greater than equals to the absolute t observed test statistics divided by n cn1. So at that time we will take the absolute values. All right. So now the computational challenge that we have, if n1 and n2 both are 20, at that time the total possible ways are 40c20, that is this one. This is the observation, that is the number of permutation that we'll have. So this number is very large. Okay, even for a total sample size of 40. So it requires a computation for around 138 billion times. All right, and it will take a long time. Okay, around maybe say 3 or 4 days continuously. And I'm saying it minimum 3 or 4 days. It may take more number of days. All right. So for larger sample, the number becomes even more large. All right. So therefore, exact permutation test is very difficult, and it is very good when the sample size is small. Roughly, we say n is should be less than equals to 30. Means if n1 plus n2 is less than equals to 30, it is useful. If it is more than 30, we should avoid it. Okay, and we should avoid the idea of uh, uh, examine all the permutation. All right. So in that situation, the solution is the Monte Carlo permutation. Okay. So instead of examine all the permutation, we randomly sample a large number of B of the permutations from the set of P, script P. Okay, from the set of script P, we will check, perform the our bootstrap on some observations. Okay, with each assignment should be equally likely. So then we compute the test statistics for each sample permutation and approximate the p-value. And this approach make the permutation test applicable to the data size of any size. All right. So we are not going to check the permutation test on each and every single value. We are going to check it on some particular number of observations. Okay. So the computation cost scale linearly with the capital B. Okay, that is your number of resampling, and the cost of computation of the test statistics with B will be very low. It will not be that much long. All right, at that time. So we have the Monte Carlo permutation algorithm here. Give me a second. I just take the photo. Okay. So in the Monte Carlo permutation test, how the algorithm will work. In the step one, we compute the original test statistic from the original data. So this step is identical to the exact test. So without permitted data, or we should say the original data, we compute the t test statistics. It can be difference of the mean, median, or anything. It will serve as the reference value against all permitted statistics that we will generate from the permutation through the Monte Carlo permutation test, and it will help to compare. It will be used to compare both of them. Okay. In the Monte Carlo procedure, T observed we use as a constant term. Okay. And after that, for B equals to 1 to B, say 10,000. All right. We perform capital B number of independent permutation cycles. Each cycle produce one T star B. Okay. And the choice of B determines the uh, how many, how much precise P value we want. So we should take the capital B a large enough at that time. Okay. After that, in that one, we need to do the randomly shuffled the pool data. So the pool data that we have Z equals to x1, x2 up to x n1, and y1, y2 up to y, and to this data we will reshuffle this data set. Okay, and after reshuffling it, and we randomly reorder the indexes of the Z and assign the first and one observation to group 1, and remaining we will use for the group 2. Okay, so generally in practice what we do, we create the label vector of length n with n1 denoted by 1 and n2 denoted by 0. Okay, and then randomly do the permutation of this vector, and the test statistics is recomputed using the original data, but with this new label assignment. Okay, so the data values itself are never altered, only the grouping is rearranged at that time. So this is the basically this respects the conditioning on the observed data, and after assigning n1, rest we will assign to the group 2, and after that we will compute the new test statistics, that is t star b, and for every group we will compute that t star 1, t star 2 and t star capital B. That will be your test statistics for all possible permutations. Okay, and this is basically called like the Monte Carlo approximation of the permutation distribution, and then we calculate the p-value here again in the similar way as we counted earlier, that is the number of count of the observations where t star b is greater than equals to t observed plus 1 divided by b plus 1, and I already explained you what is the plus 1. All right, so in that one, after that we choose the b. Okay, so p value precision is when you are taking b equals to 99, it is generally plus 1 plus minus 1 0.001, and if you are going to take it long, means more values of replication, so the p value precision is basically plus minus 0.0001. Okay, so here we have one example for that one, test statistics. Okay, that is two sample location test in the treatment, n1 is equals to 8 and 2 equals to 7, where we have these observation, and observed mean is x bar, that is 116.4, y bar is 126, and observed difference was minus 9.6. So the question is that is this difference is significant or not, and total permutation that we are going to take, that is 7 or 8 is 15, and the total permutation will be 15C8, that is 6435. These are the permutations that we are going to take. So in that one, we are going to apply the permutation test. In that, we are going to pull all 15 observation and consider one permutation. Okay, randomly assign these observations to treatment, and remaining we are going to assign to the control. If you just see here, 125 and 124 are, and these observations are from the control, but we are assigning them in treatment, and 118 and 120, these observations are from the treatment, but we are assigning them here in the control. Suppose this is one permutation that we got, and after that we are calculating their differences of their means. Okay, that comes as minus 3.46, and we are going to repeat it 6435 times for all permutations, or sample b equals to around 9999 times, and after that we will count how many t star is less than equals to t observed minus 9.6. Okay, so suppose if we are getting 52 out of 10,000, almost 10,000 replications that are greater than less than equals to minus 9.6, at that time the p value will be 52 plus 1 divided by 9999 plus 1, so it will be 0.0053. All right, so what will be the decision at that time? P value is less than 0.05. So we should reject the null hypothesis or we should accept the null hypothesis? Please tell me, we should accept the null hypothesis or we should reject the null hypothesis? Correct, we should reject the null hypothesis. So here is the R code for this problem. So we just check this one. This is the test. This is the R code for the given test, given example. So here in the treatment, we are going to store the observations. Okay. We are going to store the observation in t-test, in treatment, and in control, we are going to store the control observations. All right. So N1 is the length of the treatment and N2 is the length of the control. And then we are going to pull the both observations and combine them in the both of them in the pooled, that is treatment and control, and N capital N is equals to N1 plus N2, the length of both of them, the pooled group. Okay, and in the T observed, we are going to calculate the observed difference for the given values. Okay, and then we are going to use the Monte Carlo permutation test here. Here we are going to use the command set.seed to fix the seed, and replication is 9999 times, and T permutation in T underscore perm, we are going to store the permutations, permuted test statistics. Okay, and it will be a null vector. After that, in perm underscore that one underscore index means index, we are going to generate the sample. Okay, of random permutation. Okay, and in that one, in that one, we are going to generate the random permutations of indices 1 to capital N, and first N observations here in this one, in permutation index, first N observation we are going to take for the first group, and the remaining N1 plus 1 to capital N we are going to take as the second group, and after that we are going to take their differences. All right, and that will be stored in the capital T permutation. All right, after that we are going to calculate their p values. Okay, two-sided p values we are calculating by the sum of absolute differences of T permutation of Bootstrap, that is greater than equals to absolute values of the T observed plus 1 divided by B plus 1, and we call the observed differences in the T observed and P value. So P value is 1 into e raised to the power minus 0.4, and the observed difference is minus 9.62. Okay, and what is T permuted? We check it. So these are the observations of our T statistics of mean differences. All right. Now we just go for the another correlation test that we discussed earlier again, but this one is different one. So here we have the data of total n equals to 12 students. In X we have the study hours, and in Y we have the score that they have done in the exam, and the observed correlation is 0.68, and we want to test the correlation under the null hypothesis. Correlation is rho equals to 0, means there is no correlation, versus alternative hypothesis that rho is not equals to 0. Okay, so permutation approach, it says that under H naught X and Y both are independent, and the key point is that permuting Y values while keeping X is fixed breaks any correlation. Okay, so now what we are going to do, we will keep X as the X values as the original order, and Y we will permute. Okay, and compute the correlation between X and Y permuted as we have done earlier, and repeat B number of times. So this is the R code again that we had. So we will check this one. This code will remain same as we have done earlier. Okay, so in X we have the number of study hours, and in Y we have the scores in the test, and n is the length of X because length of X and length of Y both are same. And after that we observe the correlation between sample Pearson correlation between X and Y, and we call the correlation here. And after that we are going to use the permutation test, and we will replicate 9999 times. All right, and we are introducing the R underscore permutation as the null numeric vector of the size capital B. After that we are applying the for loop where we have the Y underscore permutation. We are going to generate the random sample of Y. Okay, because we are going to do the permutation in Y only, and other will remain same. All right, and we will store the correlation between X and permuted values of Y in R permutation, and after that we will calculate the P value as we are calculating earlier. Okay, and then we are going to calculate the permutation P value and classical P value from the core test. Okay, so classical P value is 0, and permutation T test value is again almost 0, and observed correlation is 0.987 here that we have, and we check what is our bootstrap correlation. Okay, so this is our bootstrap correlation. Sometimes we are getting negative, sometimes we are getting positive, because we are reshuffling the Y again and again. Okay, so you need to increase that one, and after that we just check. We cannot take the mean of that one. That will not be the right way to check that. Okay, so now we will move to the further. Okay, the Fisher exact test. So that we will discuss in the next class. Okay, we will keep up to here.